Okay, we're going to look at the first section of chapter 10, otherwise known for you guys as, uh, actually, it's our chapter 6, our sixth unit, but in the book it's chapter 10. And we're going to take a look at Newton's three laws. We're going to start with the first, which is Newton's first law, and we're going to find out what that really entails in just a minute. Normally, if you were in the classroom right now, you would be using this demo and you would be given a little car and a washer and you basically ram the car into the book and see what happens. So we're not in the classroom to do that, obviously, if you're watching this. So here we go. We're going to ram some cars into, in this case, my coffee mug that holds my pens. And we're going to see what happens to the washers as they go. So we're going to be looking kind of at inertia. Now, if I just push it, it's just going to stay. If I give it really hard push, do you notice that the washers stayed right where they were? They actually just fell down. It's like the car moved out from in front of them. And when we're going to look at this, is I'm going to give this a push where the washers in the car go at the same time instead of that sudden motion. And now that's why you need to wear a seatbelt because, okay, let's watch this again. Because you are moving at the same rate your car is. We made the car move really fast, and so the washer's inertia stayed where it was. They stayed where they were, the car went from underneath it. But when the car and the washers have the same momentum to start, and they go, and then the car comes to a sudden stop, now the washers, because they weren't fixed, continued to fly forward. So this is the same thing, and you guys can try this at home. If you can get a piece of cardstock and a cup and then put like a washer or something on top of it, and if you can flick that card out, you can actually make that card move faster if you can overcome the friction, and whatever on top will just fall straight down into the cup. And again, in class we would be doing that, and it works with even the car. I can flick that and make the car go into the cup as well. So really what we're talking about is pushing and pulling forces. And as we change directions, we have an unbalanced force if something speeds up, slows down, or changes direction. But it only will start moving if that force is unbalanced. If I am sitting on this chair, my body is in a balanced force position with the chair because the chair is pushing up on me. Well, gravity is pulling me down towards the ground, but the chair isn't allowing me to just fall to the ground, so I'm in a balanced force. If I were leaning against my counter, it became unbalanced because the counter didn't move, but my chair moved. But if I was just leaning here and I'm not moving and the counter's not moving, it's a balanced force. It's pushing back against me as hard as I'm pushing back against it. So imagine you were on skates and you are the same mass person and you run into each other on skates and you can manage to keep your skates flat down. You will actually bounce back, and you will both, because you have equal masses, bounce back at equal rates. If you had one person bigger than the other person, the larger mass isn't going to go backwards as much, but the little one will shoot off way farther than you would have if you're the same. So forces, both pushing in one direction, will add together to a bigger force. A little force pushing in one direction and a bigger force pushing in the other direction, so that's the big skater and the little skater, will have a net effect going in the direction of the larger force, but it is subtracting out this much resistance. So you'll notice these two small ones in the same direction got bigger, but the little one going in the opposite direction of the big one subtracts that force from the big one to end up with that same smaller force. Excuse me. Now, if I have a force of equal mass, equal force, going in opposite directions, your net force is zero because you just cancel each other out. So unbalanced forces acting on an object will change an object's motion. In other words, it can start it to accelerate. And remember, acceleration has three ways: to speed up, to slow down, or to change direction. And unbalanced forces causes those change. It causes the start of your acceleration. So here's our balanced forces. And if you look at this, you have two small arrows here, both going in the same direction, adding to a net force that is greater than each individual the sum is equal to the two small pieces. The bigger force in this direction pushing towards the female, the female not pushing quite as hard, she doesn't have quite as much mass as the male does, going that direction, means that in this case, it's classic tug of war, the more force you have is going to win. So in this case, the net force is going to be towards the right, and that's the direction the file cabinet will move. But let's say you have equal mass people, equal strength, and in this case, the left arrow going to the left is the same size as the arrow going to the right. That isn't going to go anywhere. You have a net force of 0. So this is where you are going to need to come into this set of notes. So you should actually have this set of notes up along with this video. So you'll notice it's right underneath here, because you're going to be answering some questions as we go, and you do need to turn these in. So balance forces occur when a push or a pull is countered by an equal or opposite push or pull. So is this force balanced or unbalanced? Oh, well, maybe I don't have to put and stop this. Maybe we'll just ask this in Edpuzzle. There we go. Never mind pulling that up. I'll go hide it. So you need to tell me, is this balanced or unbalanced? Take a second, answer it. All right, the arrows are going in opposite directions, but they are of equal size. So that is a balanced force. We are not going anywhere. Arg! Is this a balanced or an unbalanced force? Well, he's moving. Lucy took the football away again. So he couldn't make the football move, but his momentum kept him going, and he is, in fact, an unbalanced force. All right. This is something you're going to see on the test. So here we go. I'm going to ask you these 6 questions. You're going to have to tell me if it's balanced or unbalanced. All right, number 1. By the way, anytime you see these little swish lines, it's implying there's motion. So number 1, a ball flying through a window. Is that ball balanced or unbalanced? It's unbalanced, it's moving. Number 2, we have 2 people tugging on a rope playing tug of war. I do not see any swish lines. I do not see any movement in either direction, so it looks like they're pretty balanced in their masses. So is this balanced or unbalanced? Balanced. All right, a piano with swoosh marks, number 3. Is that balanced or unbalanced? Unbalanced. A magnet sitting there with paper clips attached to it. Now that's balanced because they're not moving anywhere. If we move that magnet just a little bit closer, all of a sudden you'd see this fly towards it because the magnetic attraction would pull it. Then it would be unbalanced until it came to a stop, and then again it's balanced. Number 5. A wood hammer with an iron head pounding in a metal nail into a piece of wood. And we see the hammers in motion, and we see that after it rebounded, that nail made some progress because there's some swish marks. Now on the test, I'll probably actually have video, but you could see a swish mark, so be aware of that. If I'm showing a swish mark, it means it's got motion. So this would have to be unbalanced. A firecracker exploding. Well, that whole shell moved away from the center, so balanced or unbalanced? Unbalanced. A balloon being inflated. Well, if the balloon's not getting any bigger, it would be balanced, but this looks like the balloon is getting larger, so it would have to be unbalanced. All right, we all know ants are pretty strong. Now, this one doesn't seem to have any swish marks. It looks like it's in its own tug of war, kind of like if I'm leaning against my counter, but I'm not moving. Well, this ant is desperately trying to pull this leaf, but it doesn't look like it's going anywhere. So balanced or unbalanced? Balanced. All right, dog and owner on leash, and they are playing tug of war. Sadly, that is not what you should ever do to a dog, by the way. That's really hard on their necks. Nor should you let them pull that hard. That's why it's really important, if you have the ability to get your dog trained well, or at least use one of the harnesses that go around their chests. That's just my plug for dog safety, by the way. All right, But in this case, we have the owner moving towards the left, the dog's being pulled towards the left, balanced or unbalanced. It's unbalanced. Now looking at number 10, the bird with a worm. But I don't see the worm moving, and I don't see the bird moving because I don't see any swish marks in either direction. So we will go ahead and say balance, that the bird is not winning right now. All right. So net force. Gotta do a little math. It's okay to use a calculator. All right. So the force of the skateboarder pushing against the ground, the force of air resistance and friction acting against the skate push. So those are kind of the frictional forces. We have some fluid friction, we have some rolling friction on the wheels and the skateboard. He is pushing with 120 newtons. By the way, force is measured in a newton, which you are going to find out very quickly here. But he's pushing with 120 newtons towards the right. The skateboard is at equal and opposite. It's pushing back with only 100 newtons of frictional force. So that skateboarder is going to be able to move towards the right. So this is really important. Not only do I need to know what the net force is, so this is straight up subtraction because they're going in opposite directions. If they're going in opposite directions, whether it's this way or this way, that's subtraction. If they're both going in the same direction, no matter what direction that is, you add them together. So in this case, 120 minus 100 is 20 newtons. And we are moving towards the right. So literally you would just plug in here, right. See how we do this? Guaranteed to have questions on like this. Two elephants pulling against a tree trunk, trying to see if they can split it. The left elephant is pulling to the left at 200 newtons. The right elephant is pulling to the right with 200 newtons. They are balanced. The net force therefore is 0, and there is no motion. Okay? All right. Person leaning against the wall, like I'm leaning against my counter, I'm leaning against my chair or my table. He is pushing against the wall with 100 newtons of force. The wall is pushing back with 100 newtons of force. Now, the wall isn't all of a sudden, falling towards him. It's not punching back. So it's going to apply as much force on the person as the person applies on the wall, unless the person pushed it over and then it's unbalanced. But right now, it's a balanced force. 100 minus 100 is 0, and no motion is occurring. All right. All right. In this case, gravity is pulling down with 100 newtons of force. Air resistance is increasing. So pushing up against the person with 25 newtons of force. So in this case, the net direction is going to be which one? Think about that. Is she going to fall up or is she going to fall down? And 100 minus 25 is 75. And the direction is therefore down. See how we do this? Again, guaranteed test question just like this. All right. So we were leading up to it, but here is the official first law of motion according to Newton. Newton's first law of motion states that an object at rest will remain at rest, and an object that is moving at a constant velocity will continue moving at a constant velocity unless acted upon by an unbalanced force, which is a fancy way for saying inertia. Basically, think about this. An object in motion will stay in motion, an object at rest will stay in rest unless an outside force acts on it. So if you're moving, you're going to keep moving forward. So if you're out in outer space in space shuttle and you push away from the space shuttle and you're not tethered, you will continue moving away from it forever because you don't have any means, unless you have a propellant on your back, to move back towards it. That's why we're tethered. So inertia is the tendency of an object to resist change in its motion. The more mass it has, the more it resists change. So we have sumo wrestlers, one in training, one that's a little more developed. Who is going to win if they run at each other? Whose momentum will be absorbed? Well, he will absorb all his momentum and push it back out, and he's not going to move, but the little kid is going to probably fly backwards with as much force as he put in. Again, all right, who's going to win? The Mack truck or the Mini Cooper? If you have a head-on collision, that Mini Cooper is going to be crushed. There's so much more momentum in that truck. There's so much more mass that it will continue forward. Now, it can either crush the Mini Cooper or completely slam it back like those washers did when we slammed it into the cup. Now, normally in class, and I didn't have anyone who could find or that had the video. I'm sorry about that. If I can find it sometime this unit, I'll see if I can get it and then we'll share it. But I take a glass of water and I put it on a platform with string and I twirl it around my head, and interestingly enough, the water stays in the bucket. Now, right after this notes, I did find a video explaining that, so you're actually going to watch that. It's centripetal force. That's what you're going to figure out. And then the other demo I generally do in the class this day is the tablecloth demo. And again, I know somebody took video of me doing that last year. If we can find it, I will throw it on and you guys can look at it. But the trick is you want to actually have a little mass in your glass, a little bit of water. It helps. And we're going to watch a video clip in a moment from Mythbusters. Well, actually, it's the precursor to Mythbusters. This is what caused Mythbusters to do the whole show on this. And I'm actually going to get rid of that so I don't get into copyright issues. But this is the trick, and it is totally plausible. One thing you never want to have is a hem on your tablecloth, because that will cause an unbalanced force to happen. It will cause your glassware to, well, fall over. And they're cheating on this, by the way. That's what Mythbusters figured out. They're using a motorcycle, and it's totally cool to watch. And once it's done, I will explain what the cheat is. Here they go. And there goes the tablecloth. What they finally figured out, they could get it to work. They could leave part of the table with a motorcycle going fast enough, but there was always just a little bit of a jerk going that fast that caused some of the items to fall over. What they did on here is they cheated. On the very far end, they actually screwed down a really thin piece of plastic that was really slippery. The table was really slippery, and they actually put the tablecloth between the table and that piece of plastic, and then set the table on the plastic, so it actually wasn't dislodging that. So one of the things you need to know, and I went past it, is in Newton's law, that tendency to resist change, that inertia in an object, because there wasn't anything really rippling underneath it for a long distance, those place settings did stay intact, especially since they were on the plastic instead of on the cloth. It is totally possible to do that trick. In fact, I've done it for years. But again, if you try this at home, never ever can there be a hem on it, because the hem will cause catching on your stemware and it will fall over. And also, please do not try this at home with your best parents or guardians china, or whoever it is that you happen to live with. Try it with a can or something if you want to try it. Try it with a piece of cloth that's slippery. It's got some nice, it doesn't have to be completely slippery. It needs to be thick enough to have some resistance. And the trick is, when you do it, is to pull and don't go up, because you will dislodge it, but to pull straight and then go down. And you can make that work. Again, I'm hoping somebody will find that video. So that's my plea. Ask your friends, ask your siblings if you have somebody that's a year older, and see if they know who took video of that last year. So Newton's first law is basically the law of inertia. An object at rest will stay at rest. An object in motion is going to stay in motion unless an unbalanced force changes it. On Earth, we have friction. So most of the time, if you are on a bike or a rollerblades or a skateboard and you push off and you will start moving forward, you will eventually start to slow down because of the rolling friction of the wheels on the road, and a little bit because of air resistance. That's more negligible compared, it is a component, but compared to the wheel friction, so that's rolling friction. And we're getting slowed down also if you're going uphill, because you're fighting gravity. So there's multiple ways to do it, but an object at rest stays at rest. An object in motion stays in motion unless an unbalanced force hits it. As always, if any of this needs more explaining, please ask for help.